Hello, and welcome to the webinar, Energy Optimization Battery Electric Off-Highway Vehicles, sponsored by Parker. I'm Chris Favre, and I'm the editor for OEM Off-Highway, and I'm happy to join you as the moderator for this webinar, as well as all of the webinars we have showcased during this year's OEM Industry Summit. Before we get started, here are a few tips to get the best experience during today's webinar. On your screen, there should be a tool on the left-hand side of your screen for you to enter and submit questions. Please type in your questions throughout the webinar. We've set some time at the end for our expert panelists to get through as many as we can. There's a box within the platform with some additional content from Parker. Please take a minute after the webinar as well to complete the survey that can also be found on the audience console. Today's webinar is being recorded and will be on demand within 24 hours. You can find it through the link that was sent to you from registering or on the OEM Off-Highway website. Let me briefly introduce today's expert, Jay Schultz, the Business Development Manager of Electrification for Parker. He has spent his career at Parker Hannifin, holding various positions in engineering, sales management, marketing, and program management. In his current role, Jay is responsible for bringing Parker's electrification technologies to market, helping to define new product platforms, and managing large customer programs. And he has a Bachelor of Science in Mechanical Engineering from the Milwaukee School of Engineering. Welcome, Jay. Thanks for joining us.
Thank you very much. Glad to be here. Welcome, everybody. I hope you enjoyed today's webinar. And with that, I will get us kicked off. So real quick, what we're going to talk about today is, one, the importance of energy management, why it matters, and some of the technical challenges that prevent us from truly managing our energy effectively, some of the solutions and ways that we can get around that and improve the energy utilization within our off-highway vehicles, and then going to conclude with some key takeaways for our energy management utilization. So, importance of energy management. Why do we even care? Well, first of all, maximizing operational time and performance. That is, of course, critical. In battery electric vehicles, particularly off-highway vehicles, runtime and performance are key critical aspects. If they don't run for very long, they're not very useful. Therefore, our customers and our fleets are not going to implement them in their toolbook. Adapting to variable loads and operating conditions. Obviously, the current diesel-powered, internal combustion engine-powered units are very adaptable to loads. They can operate in any condition that they're designed for. They're very versatile, and so electrified equipment needs to be able to adapt to those same type of environment, and some of those can be very challenging. And so we need to effectively manage our energy so we can utilize these pieces of equipment in varying conditions. Optimizing energy recovery systems. That's another important aspect. So a lot of current platforms not utilizing energy recovery systems to the utmost. And so as such, the energy that is in the batteries are not being used to the full extent. So we're going to talk a little bit about energy recovery and how that can improve runtime. Reducing energy consumption and operating costs. So by properly managing energy in your battery electric vehicle, we're able to reduce overall energy consumption and then reduce battery size potentially to be able to operate the vehicle for extended periods of time. We reduce operating costs by drawing less energy out of that battery capacity that we already have. But it's energy management is an effective or an important aspect to being able to lower your operational costs on the piece of equipment. And then enhance battery life and reduce degradation. Batteries are obviously one of the most, if not the most expensive portion of the electric vehicle, and they are very important to maintain health. And so by managing energy effectively, we're able to increase the life of batteries as well as reduce the degradation of them, so the performance while using them will be optimal throughout the majority of the lifetime of the piece of machine. And then safety and reliability. So effective energy management also plays into that. So cooling systems and how you're cooling batteries and managing that energy flow to the various parts of the hydraulic system or other areas can play into safety and reliability as well. So all of these areas here really are impacted by energy management, and by effectively managing the energy, we can bring more optimization to these aspects. Now, I'm not going to cover all of these in detail today, but I am going to focus on a few of them. But before I do that, I'll set the stage a little bit about what we will be talking about over the remaining time. So let's take, for example, a medium-sized excavator, diesel powered. Typically in that range, it's about 130 kilowatt engine or 200 horsepower. And let's look at a normalized duty cycle. And so if you take a duty cycle of an engine, and this particularly duty cycle is a publicly available duty cycle that we can get on excavators. And so there's no customer data, proprietary data that's shown here today. But if we normalize that and to put this into perspective from flow and pressure over time, you can see that the demand varies quite a bit over the course of this 20-minute duty cycle. And so repeating that over the course of a day can really demand different types of energy at different points during the operating cycle. And so if we look at kind of what it would look like from some of the engine and fuel perspective, in this size of an excavator, the fuel capacity is approximately 321 liters. That's typical of this size of a 200 horsepower, 130 kilowatt engine excavator. And diesel energy is approximately 10 kilowatt hours per liter. So we know that that's how much energy is actually in diesel itself, which then energy per tank is about 3,200 kilowatt hours in that tank. So if we look at what the energy would be needed for the duty cycle that I just showed you up above, over 8 hours, it would be 1,862 kilowatt hours of total energy. So a little bit over half of the tank of diesel fuel would be needed to work this excavator over that 8-hour duty cycle. And so it's about 186 total liters used. So if we were to force ourselves into only using battery capacity in the same volume as the fuel tank is today, we could only put in about 90 kilowatt hours of batteries. And so again, essentially, that's just an arbitrary limit right now for the purposes of the remainder of this presentation. We're just assuming in a battery electric version of this excavator, we 100% have whatever volume the diesel would take up. And so that equals about 90 kilowatt hours of storage capacity. And so as we look at that, we know that, as I just mentioned, the diesel runtime is about 8 hours, right? We can get 8 hours out of well, a little bit more than half of that tank. So what could we get in terms of runtime out of a 90 kilowatt hour battery pack? Well, we don't really know. You know, that's the runtime gap. And so the goal, I believe, for us as engineers and as suppliers is to figure out how can we close the gap between a battery electric machine and a diesel machine, given the limitations of perhaps the smallest battery pack possible to make our machines more cost effective. And so that's what we're going to talk about a little bit here. And so what are the challenges now to overcome? Well, first of all, battery limitations. That's a huge part of it, right? There's been a lot of advancements in battery technology over the last 15 years, but there still is a lot of limitations, and there's a lot of opportunity and things coming down the technology roadmap that are exciting. But today, we still have to deal with that. As I mentioned earlier, thermal management. Thermal management is not an easy task. You've got a lot of different systems to cool, whether it be the batteries, the electrified systems, the hydraulics, a lot of things, that the cabs even, right? There's a lot of different types of cooling demands and thermal management demands on these pieces of equipment. And so that's a challenge. Component challenges themselves, right? What hydraulics are you going to choose? What motors are you going to choose? Packaging the existing actuators within the systems, and other types of components that need to be implemented alongside of the electrified system. And these are all challenges that exist today. And so navigating the landscape of possible components out there can be a bit daunting. Charging infrastructure. A lot of times these types of equipment, off-road equipment, need to be operated far away from any type of grid. And so that is going to be an ongoing challenge for a lot of different types of platforms here into the future. But it is something that is important and is a challenge in energy utilization and management. And then energy recovery. That's an important thing that is not being well utilized today, and it does cause a little bit increase of bill of materials and some complexity in terms of how you architect your system. But energy recovery is a really good tool in the toolbox to be able to utilize energy management, but it is a challenge to try to utilize it in the best way possible. And then finally, complex software. So with electrified systems and batteries and all of the areas where the power needs to go to efficiently and effectively, that drives complexity into our software systems for the machine control across the board to all of the individual components as well. And so these are some of the areas that really are holding us back. And we're not going to talk about all of them today. Going to focus on just a few, actually, to bring us through this presentation. And we're going to talk about energy management and real-time energy monitoring, component challenges, and what specifically within the component challenges, motor and hydraulic systems optimization. So we can look at those portions of it and see what we can do there. And then a little bit on energy recovery and how we can essentially reuse the expended energy that was used for some work, and then recover that into the battery system for future use. These are the three areas that really can help us move forward, low-hanging fruit, if you will. And so I want to start real quick by giving an example from my own personal life. Many years ago, my first electric vehicle was a 2012 Ford Focus Electric in 2012. And you look at that battery capacity, 23 kilowatt hours of capacity is tiny compared to electric vehicles today, on-road electric vehicles. And the stated range was 76 miles. And so, the first thing I noticed right in that car, there was a very limited amount of real-time energy management tools on board. Basically, the only thing that was there was battery percentage, and that was pretty much it. Everything else was not very useful, but luckily the state of charge as a percentage was the one tool that was there. And so, back then, because of the limited amount of capacity and the limited range that you got, range anxiety was pretty much 100% of the time, unless you were driving to the coffee shop right next to your house. But in general, it was always in the back of your mind. Not so much today in modern day electric cars, but then you did. So data collection was an important part of what I needed to do to ease up that range anxiety. And so I needed to measure some things. I would go out on the freeway, go out on different roads. I could measure speed through the speedometer, time on a stopwatch, and then battery state of charge as a percentage. And what I found out through that was that I had about 59 miles of range at freeway speed. So that's not very much, but it was something, right? I knew I could operate that vehicle for that period of time and get that miles. But what happens when I needed to do something that was different outside of that? For example, I lived in Northern California at the time, north of San Francisco. I needed to drive to San Jose in a single day, and I could not stop to charge. I needed to go 88 miles. And so my point in all this is that I was able to accomplish this task to go 88 miles roughly in that day going from Rohnert Park, California to San Jose because of this need, or because of this, I understood what my machine, in this case, the car, could do. I understood its capabilities, and I had taken the data necessary ahead of time and was able to figure out what I needed to do and what I needed to change in real time to be able to extend that vehicle's usage, essentially from a distance perspective from 59 to 88 miles. And so it's an important thing to note here in this type of environment, even though we're talking about off-road equipment, the point is the same in that the tools that we have to measure, collect, and make real-time decisions are quite important. And so as we talk about real-time energy monitoring, just think about that story that I said, and then how we can implement that into our off-road vehicles. First of all, the components, that's an important part of it. Sensors and data acquisition systems really are the backbone of real-time energy management. Without sensors and without good acquisition systems, you're not going to be able to collect the data that's needed in order to make real-time decisions. And then energy management software. So then the software itself would be in place to maybe collect that data and present it in a form, maybe rough and raw data that would be fed into control algorithms that may or may not do something with it in real time, depending on how you architect that portion of it. And then obviously the user interface, and that's pretty much all that I had in that prior, in my example, is a user interface. I didn't have a lot of data, and I just had a user interface that gave me minimal types of information. But it's important to understand that the more information that we can push in up to the users through that interface, especially if we can give them the tools or the methods to be able to make decisions to extend the operating time and make more use of the energy that you have. They can make those real-time decisions. How does real-time energy management work? Well, also you have dynamic power allocation. So different types of systems within the electrified systems are going to demand power differently at different times. There's a duty cycle, obviously, and so you're going to have to be able to allocate power from one portion of the vehicle to another portion of the vehicle, one system to the other system. Load balancing plays right into that too, because the power requirement needs to be changed and dynamically allocated. That also implies that loads need to be balanced as well, whether it's a physical load or electrical load or other types of load on this cooling load on the system. All those need to be considered and understood. Regenerative energy, how that comes back into the system, needs to be managed as well. And that's part of understanding where energy flow is going and load balancing, what could be recovered and what may not be able to recover. And then thermal management. Heat is the enemy of performance in a lot of these systems. And so we need to make sure that our thermal management systems are being monitored correctly and that we're understanding what our capabilities are from a coolant system to get the most out of it. And so those are important concepts to understand and to delve deeper into as we're understanding more about real-time energy management. And then utilizing some advanced technologies in order to really gain the benefits from the first two portions of that. Artificial intelligence and machine learning, huge area of growth in a lot of different market segments. It's the same here in our area in electrification, what we're doing. There's a lot of things that AI and machine learning can do to help analyze data, to be able to help with decision making, etc. Digital twins is an important advanced technology to utilize as well, making sure all of your models and everything that you're designing in real life is digital identical on your computers and design platforms, so you can understand and simulate and do things ahead of time before you actually build it. And so that's an important thing that a lot of customers are just now scratching the surface of to be able to implement. And then cloud-based IoT systems. A lot of IoT systems out there are very valuable in terms of collecting or help collect the data and pushing it up to the design teams, pushing it to the customers or fleets to make, again, real-time decisions on how the energy is being utilized, how the vehicle can best perform, et cetera. And so these are all things that are very important to grasp as we try to manage our energy and get the most out of our energy that we have in our very limited amount of battery capacity. So want to talk about that a little bit more now. And first thing is, you know, as I mentioned, know your system. Understand where it's coming from, where your power is going, and we do that through instrumentation and through the sensors that I mentioned in the prior slide. We want to monitor things like engine torque, engine RPM, in your baseline system to make sure that you know what the diesel engine is providing and the diesel system is providing to all of your different hydraulic systems, so you know where the opportunities are. So once you've instrumented your system, you're measuring hydraulics, flow, pressure, and even oil temp. That's all being collected in the raw data, and you have your algorithms and control software to figure out how to collect that and putting it into a meaningful way. Perhaps then you graph it and look at it at each function level, whether there's 3 functions here or 5 or 6 or 7 different functions. So we understand where the power is going, and then from there you can create your own individual performance indicators to see opportunities and where are those areas of potential high losses or low efficiencies, or areas where you may be able to improve not only from an electrified system perspective, but also from maybe a hydraulic architecture perspective. And so we're really trying to understand what the pressures and flows are at the pump outlets, at the valve inlets, flow at each actuator, and as well as distance traveled. So we truly can understand the amount of energy that's flowing from the energy source through the system that's actually then being put into work. So when you think about how much energy is being utilized that actually goes into work, it's dramatic how the losses in the system can pick away at your overall energy consumption. So if we just look at those losses now, and we look at this current state with this particular duty cycle, as I mentioned, for an 8-hour duty cycle, for an 8-hour run of that duty cycle, we use approximately 1,862 kilowatt hours of energy needed in diesel fuel at the gas tank. So once we put that through the engine, that's turned into shaft power. A huge percentage of that is lost just in the efficiency of the internal combustion engine. We get 651 kilowatt hours of energy that's left now from a shaft perspective to go through and do work. From there, we have losses in the pumps. Not a lot there, but there is some losses there. And then from the pumps through the hydraulic architecture, we have an additional set of losses. And so our losses are added up here. So we have approximately 1,200 losses to the engine, 66 kilowatt hours of losses to the pump. So not a lot, but some. The downstream hydraulic architecture and systems losses are 402 kilowatt hours, which leads us to essentially 189 kilowatt hours of energy that actually goes into useful work. And so 90% of our initial energy in our diesel fuel is lost to losses before we actually get to doing the useful work. And so it's a pretty incredible amount there when you look and you break it up into kilowatt hours. And so if we look at this now, what can we do to decrease the energy consumption across the board? So obviously electrified systems, right? We're going to get rid of the engine and we're going to improve the efficiency of the prime mover by utilizing an electric prime mover and inverter system. We can now also look at the pumps. What can we do there? Even though it's a relatively small amount of losses in the pumps itself, there is some opportunity by choosing perhaps a more improved pump efficiency. And then the next portion is looking at the hydraulics. What's our opportunity from a hydraulics perspective re-architecting it and maybe doing some things there, that is a pretty significant amount. Maybe half of the potential losses can be recovered there by improving downstream systems and controls. And then finally, what can we do to itself in the useful work? And that is recapturing some of the energy that we're putting into useful work so we can reutilize it again. So we're not necessarily reducing the total amount here of work. We're just getting some of it back that we've already used. And so these are some of the key areas that we can look at, obviously, to be able to get more runtime out of our battery pack instead of utilizing other traditional mechanisms. And so let's look at these a little bit closer. The motor and inverter section, right? So we're improving the prime mover from an internal combustion engine to an electric motor. And so motor design matters. There's a lot of different designs out there, but picking the right motor is not just as simply, oh, I'm just going to grab this motor out of a catalog and implement it in my system and away we go. Actually, the motors out there, permanent magnet motors, comparing all of the different architectures are not the same. So one permanent magnet motor that's designed for mobile equipment versus another permanent magnet motor that's also designed for permanent equipment could have as much as 15 to 25 kilowatt hours of additional losses per this 8-hour duty cycle. And so that's a lot of battery capacity that you need to pay for in the system if you're just, if all else being equal, one motor from another. And so it's important to look at things like distributed windings versus concentrated windings and saliency versus non-saliency. There's some technical terms that I'm not going to go into, but all of these things matter when you're talking about the component optimization within the prime mover itself. And so I just want to reiterate that not all electric motors or electrified systems are the same in terms of the components themselves. But to be clear, any e-motor is a huge improvement over an internal combustion engine, period. You could use a DC motor, and that's going to be better than your internal combustion engine. But most of the marketplace in this day and age is going towards internal permanent magnet motors. So it's important to look and see those and how they differ from one another. I'm just going to throw up here 2 examples, and this is an example from our lab that we did when duty cycle was considered. The top one was a Parker motor. Excuse me, the top one was a competitive motor to Parker, and only 40% of that operating zone was over 85% efficient. And you look at the bottom motor, 65% of the operating zone was over 85% efficient. So when you look at those 2 things and you're considering duty cycle, even though the catalog of these 2 motors showed the same peak efficiency number, when you're looking at how the entire motor is designed, it can have vast differences on how much energy is consumed over a particular duty cycle. So the next set is pumps. And as I mentioned, pumps have a relatively low amount of potential that we can recover, but there is something there. And so as long as we're looking at all of it, let's just talk about it a little bit. So if we move across the spectrum from pumps, you've got gear pumps or different types of pump technologies that are a little bit lower on the efficiency, all the way up to bent axis pumps, which are much higher on the efficiency side. And so, looking at those efficiencies matter, because even if the pump is a few $100s more expensive, when you're talking about the implications of runtime on a diesel or runtime on a battery electric piece of mobile equipment, that is a very small cost to pay for when you're talking about runtime and battery capacity and battery total cell counts. And so within the pumps themselves, there's also some things we can do to improve energy management, and that would be things like battery saver algorithms. So by having a pump that is either variable displacement or a motor that can then change speeds, you can get into a point where you can save on battery and save on energy allocations if you're getting to a point where you need to. And then things like hush algorithms as well. So that, while that's not necessarily relevant for energy management, it is an important part of the overall control system and architecture and how the machine operates to be able to reduce audible noise at times. And so given the control of the electrified system's ability to control pumps very, very effectively, you can have different types of software controls that can help both with efficiency as well as some other aspects of the system as well. Architecture. And so this was an area that had a fair amount of opportunity in it. And so by looking at the architecture of the system, and we're trying to optimize it through, from the original design of the internal combustion engine all the way over to maybe maximum efficiency, there's a lot of aspects to this. And so this is kind of a busy slide here, but if you bear with me for a moment, on the far left-hand side, you have an internal combustion engine and some type of pumping system, and that those typically go into a control valve or several control valves, and then out to your various functions. And so that's a lot of times how it's architected. And so in the simplest, easiest, most straightforward way of creating an electrified machine, you simply take out that internal combustion engine and you put in an electric motor, which is a very valid thing to do, and a lot of companies do it for their first round. And you put some pump mechanism on there, and you go keep your hydraulics largely the same, and it's a single system that has already been designed. And so that's great for the first iteration. But as I mentioned, and maybe you can infer that that's not always the most efficient way, especially when you're talking about battery capacity and then the runtime slot of that. So as you go a little bit more efficient, you can add maybe another EHP, which is a motor and a pump combination. So then you'd have two motor pump combinations with maybe a more complex control valve architecture, which gives you a little bit more controllability in terms of your hydraulics. You can do some things there to reduce the overall losses, which is a good improvement there. But you've increased the cost by adding two electrified motor pump systems instead of just one, with arguably not maybe a lot of gain. And as you go further to the right on this slide, you're adding more and more systems and separating the hydraulic systems or re-architecting the hydraulic systems so that you not only can get more efficient, but you can also start to recapture energy. And so those green arrows that you see on the right two portions are actually showing energy recovery going from an implement or from some type of hydraulic system back through the valving, back into the electrohydraulic pump, and then back into the battery system. So that's the energy recapture. And so you can see there that typically to have an energy recapture system, you need to have one motor pump system per function so that you can recapture that potential energy. And so that's an important distinction to make. And in doing this, as you are increasing the system performance and efficiency, you also inherently increase the complexity and the cost. So that's the downside. But as you'll see, hopefully, the argument that's made to doing some of this, to re-architecting your hydraulics, will actually pay dividends in terms of energy utilization. So again, from a system architecture perspective, open center valving systems from just a real high level, you have a lot of power wasted by just continuously providing flow when you may or may not need it. As you move to a more advanced system, a load sense system, there is a lot of energy benefits there in terms of getting rid of losses, but you still have some power wasted, and there's different types of losses in those systems as well, even though it's a huge step forward. And what you really have difficulty time doing in a true load sense is to utilize energy recovery systems. And so the next portion would be flow on demand. And flow on demand is an entire can of worms in and of itself. But by implementing flow on demand, you open yourself up to a new architecture that allows for utmost efficiency through energy recapturing. And so that's an important distinction and thoughts to make as you're moving through the architecture world. The next aspect is energy recovery. And so that's obviously trying to get energy back that you've already used. And so this is an advanced hydraulic system that needs to be thought through from the beginning. And it needs 2 or 4 quadrant pumps in order to be able to send that kinetic energy or releasing of potential energy back into the battery system. And so it's an important thing to remember that not any pump will work. And so by capturing this energy back, we can not really reduce the amount of energy consumed, but we can recapture it and put it back into the energy system so we can utilize it again later. And so a great example of this for an excavator would be like the swing drive deceleration. That is a huge load. It's very repeatable, a great way to get a fair amount of energy back into the system. Vehicle regenerative braking. Now, not all off-road vehicles are able to utilize regenerative braking, but there are some that definitely can. And so if your vehicle can do that, that is a very, very good way to leverage some energy recovery. And then, of course, lowering a suspended load and having gravity be a help to put energy back into our systems. And so the next portion of this here is going to look at where are we at. So we talked about a number of different solutions and possibilities. So if we go back to the example now, originally we used 1,862 kilowatt hours of diesel. We take out the losses of the internal combustion engine, so we're removing 1,211 kilowatt hours of losses, but we're putting back in losses for the motor and inverter system, which is 57 kilowatt hours. And remember, 57 kilowatt hours is an estimate. Depending on the electrified motor system, that could be up to 75 kilowatt hours or even more. So it's important to look at that portion of it. But again, any e-motor, as I mentioned, is going to be better than internal combustion engine. So if that's all we do and we take out the engine and we put in an electric motor, we're going to only get a little over an hour's worth of runtime because we're going to need 708 kilowatt hours of energy in order to to do that full battery or do that full duty cycle. And so that's just not going to work. A 1 hour only. And so what are these other options that I talked about? What will that give us? So if we just then change the pump, as I mentioned, there is some aspects to pump. It is going to give us something back, but not a tremendous amount here, right? So you got about 6 minutes if you just change from, say, a traditional gear pump running at constant speed or some flow over to a more efficient pump. You're going to just get a little bit of energy back. But then you actually change the architecture a little bit and you go to flow on demand. Now we're still running the system at a constant speed. So the motor is really running at near constant speed. And now we only change the displacement on the pump, and we can utilize a lot more energy there. We get rid of a lot more losses. And so we add an additional 1.2 hours of runtime just by changing our architecture and utilizing flow on demand. And so I just want to note here that these are all additive. So if we jump from the motor and inverter system directly to the variable displacement pump, that is inclusive of the energy savings that we get by moving to the bent axis. So this is like a waterfall diagram, and so it's all inclusive here. And so you get an additional 1.2 hours. So now you're up to almost an hour and a half of additional runtime that you've got just through changing the architecture. And so then the next step we look at is adding some variable speeds to this. So now we're doing the same thing. We still have a different architecture and we're still going through flow on demand, but now instead of perhaps a variable displacement pump, we're using a gear pump or a bent axis pump with flow on demand. And so these opens up a number of architecture discussions that are beyond the scope of today's call, but by utilizing a variable speed now in the motor, and by architecting to use either a gear pump or a bent axis pump as flow on demand, you're able to get an additional almost, about 0.25 hours of energy recovery back. or fewer losses of added runtime. So now we're at a total of 2.56 hours of energy needed or runtime for our 90 kilowatt hour battery pack, right? So we're limiting ourselves to this 90 kilowatt hours of battery pack. So then the very last thing that we're going to add to this, and I'll say that the flow on demand through these various architectures is the enabling factor here to recover energy. By now going to the energy recovery implementation, we're able to increase our runtime again by an additional 1.25 hours. And so our total now, if you add all this up by taking the engine out, putting an electric motor in, and jumping all the way to a variable speed flow on demand architecture that implements energy recovery, our total utilization now, our total runtime is 3.81 hours, and to achieve that 189 hour or kilowatt hours of work. And so for a full 88-hour duty cycle, we would need to increase our battery capacity from 90 to 189 kilowatt hours, but we've made a huge amount of progress. If you look at where we were by just simply keeping the hydraulic architectures the same, pulling out the internal combustion engine and putting in the motor, we've gained over 2.5 hours of runtime by changing that. So we have massively increased the benefit or our energy utilization within the battery pack. And again, as I mentioned, batteries are very expensive. So in my opinion, this type of discussion is very important and to look at when you're talking about utilizing the battery capacity to its most effective means. And so what is the runtime now that we're achieving, trying to close the gap? We didn't close it all completely with just our architectural change and 90 kilowatt hours. But what we did do was we reduced it to 4.2 hour gap. And so as I mentioned, in order to get a full runtime, the full days of work out of it, you would only have to double your battery capacity. And I've seen excavators out there on the marketplace with 320 kilowatt hours of battery pack, which makes complete sense if the hydraulic systems haven't been re-architected to utilize any of this. And 189 kilowatt hour battery pack for an 8-hour duty cycle is a lot less expensive than 350 kilowatt hours, that's for sure. So by implementing some of these architectural and product changes, you're able to lessen the amount of expense of your battery pack, but more importantly, in my opinion, is to make the machine more useful to our customers and to the fleets out there that are actually trying to do work so that they are valuable. Because if it only does an hour's worth of work or it's exorbitantly expensive because there's so much battery on it, one, they're not going to get purchased, or two, they're not going to be very useful because they're going to need a diesel system right alongside it anyway. And so it's important from my perspective to consider some of these things so that we're engineering vehicles that actually do the job. So I want to take a moment here before I go into the closing remarks and just throw out here to the audience, what topic would you like to explore in greater depth for an upcoming webinar? And these topics here are part of the things that I talked about here today that we could go into much more detail instead of glossing over there. So please select A, B, or C and then click submit, and I will move on in a little bit. So for example, if you wanted to select energy recovery systems, we could spend 30 minutes, 45 minutes really delving into how to implement energy recovery for an electrified machine, what systems would be required. We talked about 2 and 4 quadrant pumps, what would we need to utilize that, and how does it work? The next portion would be control architectures for electrified hydraulics. So a few slides back, we had a number of different control architectures where we had the internal combustion engine with a series or a pumping system, and then a series of valves, and then the functions. And as you move to the right of that complexity, we broke that up into a number of different We call them e-pumps, EHPs, electro-hydraulic pumps, motor pump combinations. A lot of that stuff is very complex. We can spend a bunch of time delving into architectures. And then finally, motor inverter technologies. I mentioned that not all e-motors are considered the same in terms of their own architecture at the product level. And there's a lot of variations in terms of efficiencies over duty cycles, and how they're designed really can impact how much energy is wasted from the battery pack. So select one of those three that you think would be the most interesting, and click submit, and then we'll review that here on the next slide. We've got 30 of 54 submitted. I'll give it another 30 seconds or less, depending on how impatient I get. All right, so we have 43% of you said energy recovery systems would like to be explored more, 36% control architectures, and then 20% motor inverter. Okay, well, thank you very much for your feedback. Appreciate that. And now let's get into the takeaways here for the session. So the first takeaway is obviously energy usage, understanding where the energy is used and what are the associated losses. And then how does duty cycle impact both the system and the components, right? It's important to understand that. And so these are all aspects that you can spend a lot of time on trying to understand that a bit better, but that's a very important part of it. Tools. What tools can be provided to the operators to help decision-making run or extend the runtime? Just like my example back in the day when I needed to go 90 miles in a car that shouldn't have been able to do that. How can you do that? How do you get the job done? How do you give the tools, or what kind of tools can you give operators to be able to extend that runtime so ultimately the machine is more useful? Components. Look closely at all of the components. Not all components are created equally, whether it's a pump, whether they're valves, whether they're motors, inverters. It's important to take a good look at that, because that can really have a massive amount of impact on the system itself and the amount of time that you can run the vehicle for. Cost and efficiency. Obviously, cost is a huge importance in this market. I mean, battery electric systems and vehicles are pretty expensive, but the lowest cost doesn't mean much if the product isn't useful. So you may create a very low cost architecture, very low cost system, but if it only runs for a fraction of the time that the predecessor, the internal combustion engine, ran for, it doesn't make it more useful. So you have an expensive piece of equipment that can't be very useful. And supplier and technology roadmaps. I encourage you to look at the suppliers that you're choosing. What are their technology roadmaps, if they'll share them with you, so you know where they're going to help with the system's efficiencies, to help with integrating components together, to be able to really get to the end game, and that is to reduce the amount of energy storage required in order to get through a day's worth of work. So it's an important part to have the technologies. And so just want to say that, look for integrated systems. That's an important part, what suppliers are doing in terms of integrating their components together to make them more cost effective, as well as enabling energy recovery. Connected, obviously the electrified systems are electric, so they're inherently a lot more easily connected to IoT systems, etc. And then efficient. And so make sure that all your systems that you're looking at are the utmost efficient, so we can get the most amount of energy or the most amount of runtime that's necessary with the existing battery packs or the capacity that we have. And so I encourage you to go look at Parker's Smart Electrification, because we like to think that we have done some of these things. So with that, I appreciate your time very much, and we can open it up to some questions.
Yeah, thanks, Jay, for a really good presentation on electrification. So appreciate you again taking the time to go through this with us. And yeah, we have some time for the Q&A session. So attendees, if you haven't submitted your question yet, take a second, shoot those over to us using the Q&A box. And any questions we don't get to today will be collected for our presenter to answer for a post-webinar Q&A article. We have a question here asking, let's see. So you mentioned 2 and 4 quadrant pumps. How does that work with a motor? And can any hydraulic pump be used for energy recovery?
Good question. Yeah, we did mention that a little bit. And so you cannot use any hydraulic pump when you're trying to implement energy recovery. And the reason why is because when the flow is being reversed and you're trying to recapture that, and in order to recapture that, the electric motor then needs to be put in generator mode. In order for it to be put in generator mode, it essentially has to spin backwards, if you will, or create negative torque. And so that pump that you utilize has to be able to manage the flow in both directions so that you can put the negative power, if you will, on that electric motor, to make it, to turn it into a generator. So you only can use 2 and 4 quadrant pumps, and you have to look at that to see if the pump that you're selecting can do that before you're able to utilize any type of energy recovery system.
Next question is asking, in your experience, is there any systematic way to select e-motor type based on final application, or is it a choice to be done? Is it determined on a case-by-case basis?
I think there's always a systematic way to do it, and I think what we always tend to look at the system and what's the flow required ultimately, flow and pressure. And once you know your flow and pressure, you can back into essentially what kind of a motor that you would need. And so you can't, it's not necessarily this motor is great for this application, because even if it's the same kind of task that the application is doing, same type of function, there are a lot of different speed requirements, there's different load requirements, so that has an implication for how big of an e-motor you need. And so one of the things that is very confusing to people who are hydraulics experts that may not understand how the e-motors work is if they implement a hydraulic pump, for example, and they're not quite getting the flow that they need or the performance that they need on the hydraulic side, they take the pump off and they put on a larger, higher power pump with more displacement or whatever it might be, and it still doesn't work because the pump and the motor need to be sized together to accomplish whatever amount of power utilization is required by the function. So really you start there at what does the function need, and you back into what the e-motor requirements are. And so that's the best way to select it. Now, if you're talking about e-motor architecture, that's a whole nother can of worms, another discussion. But in general, you start at the final application or the final requirements for pressure and flow. You work back into your e-motor that way.
Okay, next question is, sorry, got twisted around. Which off-road equipment types would be most electrifiable from your perspective?
So good question. So off-road equipment type that would be most useful are ones that I would say have relatively low amounts of daily hours of work required. So, obviously that can be very open-ended, but, things that are running all day long, every single minute, with high power is going to be very difficult to electrify because they have so much energy requirements, especially if they're large. And so you're just no matter how efficient the system is, it's just too much energy for today's battery, even tomorrow's battery technology to be able to utilize. And so I think things that have a moderate duty cycle, that have moderate amounts of power, so we can get a sufficient amount of batteries in the architecture of the system while not going crazy in terms of cost and capacity. So, mini excavators are a great example of that because they're not necessarily used in tremendous amounts of long duty cycles, and they're smallish. They pose some challenges for packaging it all together. Skid steer loaders are a good example too, although those have their own challenges. Telehandlers and things like that that have wheels. You can do some regenerative braking on those types of equipment if it's architected correctly, as well as the energy recovery from the lowering of the lift, if that's something too. So I think certain construction equipment, certain material handling equipment are the best to electrify. Some of the ones that I think are not as easy to electrify are forestry equipment, because those tend to be way far away from any types of grid. They're used for days or weeks on end without ever going back to their home base, and they're very difficult to be able to electrify and recharge and then use again the next day. So that's an example of one that's far out. And then I guess one other type that I didn't mention would be certain types of mining equipment is really, really good as well.
Yeah. I guess, in a general sense, could you define what a 2 and 4 quadrant pump are, and what are the differences and what are the similarities?
Sure. Yeah, no problem. So 2 and 4 quadrant pumps are pumps that can basically switch between being a pump, like taking the mechanical power and converting it into hydraulics, and being a motor, which would take the hydraulic power and then converting it back into mechanical. And so it's just an architecture there of how the pump is designed, so it can essentially convert the energy sources from mechanical to hydraulic, and then hydraulic back to mechanical. That's the point of it. And so we can talk about pump design in another session too and get into more detail, but we don't have too much time for the pump design itself.
Yeah. So this will probably be our last question, but what kind of pump can work in regenerative mode, and maybe give it like an example or two?
Sure. So over center pumps are an example of what it would be, and potentially some bent axis pumps as well. And so, those are some example or some types of pump technology that can work for regenerative mode. We also do a lot of gear pumps as well, helicoidal gear pumps. Those can work in regenerative mode.
Okay. Well, I think that's going to do it for the Q&A session, bringing our webinar to a close. I'd like to thank Jay for his insights and expertise here today. So appreciate you bringing the OEM Industry Summit to a close with a really good presentation.
Thank you very much for having me.
Yeah, my pleasure as well. And attendees, you'll be receiving an email from us soon with access to today's playback and presentation. Please also feel free to visit oemoffhighway.com to check out more on this topic, and also browse other topics in our bank of educational webinars. Also, once again, please be sure to fill out our survey and let us know how we did. We take this feedback to enhance our future webinar experiences. And thanks again to Jay and Parker for and all of our attendees for taking the time to join us today. And this concludes our webinar, and this concludes the 2024 OEM Industry Summit. Thank you all who have attended so many of our presentations, and thanks again to all of our presenters over the last 3 days for giving us some great insights on the off-highway industry, to you and to us. Thank you.